Good afternoon, everyone. Welcome to today's session on Firecracker. Typically, when we talk about virtual machines, fast is not the adjective that is being used. However, we see that there's a need to create runtimes if we want to run multi-tenant workloads, at the same time also to run lightweight, secure functions or tasks in container-like environment. We want flexibility and high density with fast performance. So that is what Firecracker essentially provides. So today we will be learning about Firecracker, how it makes a secure and fast microVMs. My name is Meena Gowdar, and I also have Arun who will be joining me in today's presentation. So what is Firecracker? So Firecracker is an open source virtualization technology. It's a virtual machine manager that uses Linux kernel-based virtual machine to create and manage lightweight VMs that we started calling as microVMs. Before Firecracker, it was a hard choice that developers had to make by choosing a secure environment that had hardware virtualization-based isolation and workload security, or use container-like, lightweight, high-density C groups. But with Firecracker, you no longer have to make that choice. You get both. So Firecracker provides enhanced security and workload isolation over traditional VMs, while also enabling speed and the density of containers. It uses extremely low resource overhead, which actually makes it suitable for running serverless computing. It was developed at Amazon Web Services to improve the customer experience of services like Lambda and Fargate. When we launched Lambda in 2014, we were focused on providing a secure environment for customers to run their tasks. So what we did was we ran these tasks in single account, single task on each EC2 instance. Over time, we realized that we need a more scalable, efficient environment in addition to providing the same level of security as traditional VMs, and that's the premises of how we developed Firecracker. So taking a closer look at Lambda. So if we zoom into a single Lambda worker server, this is like a physical machine, which provides all the compute resource like CPU, memory, or other network resources. When customers pay for a specific workload function to run on the worker, we don't have visibility into when they're going to require those resources and in what succession those resource requests are going to come in. But we need to make them available. So how do we make utilization of that physical resource efficient? So if we run more and more functions on a single physical hardware, it becomes more efficient in terms of the resource utilization. But when we run multiple functions from multiple accounts on a same physical hardware, how do we ensure that one set of arbitrary binary codes from one account doesn't jeopardize the security of other environments? So that is where we need to use virtual machines. But virtual machines don't provide this level of flexibility over subscription and the nature of high mutation in a traditional sandbox environment. So Firecracker helps provide that level of flexibility and also the same security. So here are the benefits of Firecracker: security, efficiency, and performance. So how do we get that? Firecracker uses a minimal device model, which means that it only has a very limited set of functionalities and did not implement legacy device emulations as you would see in like a QEMU. So this improves security because it reduces the attack surface on the microVMs. Because of the minimal device model, it improves our startup efficiency time, and it increases our hardware resource utilization as well because of the low overhead. So let's look into what that means. So security. So Firecracker VMs, it uses the KVM-based virtualization that provides enhanced security over traditional VMs. This ensures that workloads from different end customers can safely run on the same machine. And because of the minimal device model, it also reduces the attack surface on the microVMs. Then we have speed by design. So in addition to this minimal device model, Firecracker has, it accelerates the kernel loading and provides the minimal guest kernel at a really fast pace. It only has two devices, the virtio net and virtio block, and it has few keys to do power management on the microVMs. So this enables the low overhead in terms of how much memory it requires and allows for the fast boot up of each of these microVMs. So we have done some benchmarking, and we're able to achieve up to less than 125 milliseconds to launch 150 microVMs per second in a single host. Then we talk about the scale and efficiency. So each microVM runs with a reduced memory overhead. It has less than 5 megabytes for enabling a high-density microVM, all of them packed on a single server. So the Firecracker also provides a rate limiter. The rate limiter is used to equally distribute the resources across the hundreds of VMs that can run on a single host. And then with Firecracker, you can see that we're making the same deep investment from an infrastructure standpoint for serverless compute, same way we have done with traditional EC2 instances. We started with support for Intel processors, and we are working on supporting AMD and ARM-based processors as well, and those should be coming out soon. We're also integrating Firecracker with Containerd for the container ecosystem. So let's talk a little bit about the Firecracker design principles. So Firecracker can safely run multi-tenant workloads from different customers on the same machine. So this is possible because of the hardware virtualization-based security that the microVMs offer. Customers can create microVMs of any vCPU and memory configuration to match their workload requirements. So this allows to map nicely for services like Lambda and Fargate for the different set of configurations that each of these services offer. Firecracker microVMs, it also allows oversubscription of both the compute and memory resources. So to that extent, we're able to improve the efficiency of how we are using the underlying physical resource. It also offers a steady state mutation. You can launch up to 100 microVMs per host per second, which is roughly about 4 microVMs per physical core. So if you kind of use that on a hardware that has about 36 cores, you can really spin up a lot of microVMs. So how much can you launch on a single hardware? It's only limited by the amount of resources that are available on the hardware. So at the scale of 100 plus microVMs, it really packs a lot of VMs on a single host. So each microVM exposes a host-facing API via an in-process HTTP server. And then each microVM can provide guest-facing access to host-configured metadata services, which is accessible via the MMDS API. So here's the list of APIs that are accessible through the HTTP server using on specific URLs carrying the JSON model data. The return generally returns the instance information. You can call put actions, and you can also initiate actions with them, like instance start, which spins up a new microVM. You can send control alt del. Typically, send control alt del does a a reboot in a typical Linux distribution. On the Firecracker side, when the CPU resets, the microVM exits. So it's a good way to shut down microVMs as well. We also have a block device rescan. So the block device rescan action is used to trigger a rescan on the microVM attached to the block device. After sometimes it has like the backing file has to be refreshed on the internal data structure. So this can be done after the microVM is instantiated. We also have the get machine config action that will allow you to config the microVM to any vCPU configuration, and same way with whatever memory you need for the microVM. The vCPU could be 1 or any number in even numbers, depending on the type of workload you need. And then you can call the put actions to configure all these instances as well. We also have the drive action, which will help create new drives, and you can provide a path on where to define those drives. So Firecracker, it runs in the user space, and it uses the Linux kernel-based virtual machine to create microVMs. It's fast startup time and low memory overhead. Allows each microVM to be packed really well in a single hardware. So we've been successfully able to pack thousands of microVMs in a single hardware or server. This means that every function or container gets its own microVM, its own virtual machine barrier, so in a secure environment. So in addition to having that security, because of its lightweightness, you get the experience of traditional containers. Firecracker is an alternative to QEMU, which is an established VMM with general purpose feature sets, and it can support a wide range of guest operating systems. And then here you can control the Firecracker processes by calling the RESTful API. So we have the APIs that we shared. So it has a RESTful API that has the common functions where the guest can communicate with the host. And then we also have the rate limiter that helps manage the granularity of how network and storage resources are allocated between the different microVMs. And the rate limiter also helps you to configure how you want to manage the burst experience of each of these resources within a microVM. You also have access to the metadata from the host into the guest. So that's something that the guests can communicate with the host and configure it as well. So we'll look into one of the use case on how Lambda is using Firecracker. So Lambda is a global service. We call it a foundational service available in all of AWS regions, and all new regions will offer them as well. We build our systems behind the scenes to make sure that it can distribute load, it can work around failures, it can scale up and down so that customers don't have to worry about managing their clusters and fleet. And of course, while doing all of that, we need to make sure that we preserve isolation and then maximize utilization as well so that the cost benefits are passed on to our customers. One of the primary systems that powers Lambda is called the worker. So what does the worker do? So worker, it creates and manages a collection of sandboxes. It sets the limits on the sandbox in terms of how much CPU and memory is allocated for that sandbox. It then downloads the customer's code and mounts it and gets it ready for execution. And once the initialization and invoke is called, then the customer code is executed. And also, the worker helps provide some of the AWS agents for monitoring and operations, which is like the CloudWatch tools. So here's a closer look at the architecture. So at the top, you have the customer's code, the zip file that is shared. Then we have the Lambda runtime. Lambda runtime supports many different runtimes like the Node, JS, Python, Java, and C#. So underneath the runtime, we have the sandbox that provides a copy of the guest Linux that we run. And then the guest OS is running on top of the hypervisor. It's actually multiplexed across the hardware through virtualization. So the virtualization is enabled through the hypervisor, and then the hypervisor is running on the host OS. In this case, it's the Amazon Linux that we run. Now this is running on top of the physical server. So to keep the workload safe and separate, code and runtime and sandbox are usually one function. So one function comprises of the customer's code running its runtime within one sandbox. So we never share that sandbox with multiple accounts or multiple functions. And then each of these functions within a sandbox is kind of, if you invoke the functions, they're always sequentially arranged in the same sandbox. Then we have the guest OS systems that is shared across multiple accounts, and there's never one sandbox shared between multiple accounts. So the 1:n mapping of the multiple AWS accounts on EC2 instances or other equivalent hypervisor on which it is running. So then we have the boundary that we put between the different account is the virtualization layer. So there are two types of virtualization layer that we offer today. One is the EC2 virtualization that is traditional, and then here the other one is the Firecracker. So Firecracker is a virtualization that is provided on a bare metal instance. This is very similar to a bare metal instance that you will be able to access from our EC2 console that provides the high performance for these functions. So this really simplifies the security model for us by using microVMs and placing each function within a single microVM. And so we're able to run multiple accounts, so one function per account in each microVMs allocated to multiple accounts running on the same physical hardware helps us to improve efficiency. This is also a good programming model because it provides good isolation between all the individual functions as well. Another optimization that we do is how we pack these workloads. Typically, customers think that we take same type of workloads and then create multiple sandboxes in a single hardware and then run the same type of workloads on the same hardware. It turns out if you're running same workload on the same physical server, they're going to have a very correlated pattern of how resources are being used in terms of bursting at the same time and then being idle at the same time. So if we truly want to maximize our utilization, we want to do a spread placement that allows placement of uncorrelated workloads across multiple or a fleet of servers so that we are doing a real good bin packing of workloads that require different resources and having more utilization. So this really helps us to make sure that we also have a secure boundary for functions while being able to provide a high performance, fast-acting, container-like environment for our tasks and functions. So I'll pass it on to Arun to talk about the container ecosystem.
All right, so my name is Arun Gupta. I'm working the open source team at Amazon. Now, let's take a look at it, how Firecracker integrates with containers. What are the ways by which you can look at it? Now, if you look at what does AWS offer in terms of containers, we look at it from three different perspectives. First is the management. So you're looking at Amazon ECS, which is a service that we launched back in 2014. which is when Docker was young. There was no Kubernetes. Customers wanted to run Docker at scale, and that's why we launched a fully managed container orchestrator for you. Customers love Kubernetes. More than 50% of Kubernetes runs on AWS, but they wanted us to provide a managed service. That's the reason we launched Amazon EKS. Last year, it went GA. So those are sort of from the management perspective. Then under the hood, you could run them on EC2. That means we provide a control plane, and you bring your data plane and attach it to the control plane, and you run it that way. Now, AWS Fargate is an innovative technology which really allows you to say, you want to run containers, you don't want to focus on the undifferentiated heavy lifting, you just want to build apps and let somebody else manage the containers, whatever it is for you. So AWS Fargate is a mechanism by which you say, here is my container, run it, scale it, monitor it, debug it, things need to happen, just do it for me. So today, if you think about Amazon ECS and EKS, they both run using Amazon EC2, that means control plane manage, bring your data plane. And ECS today also work with Fargate. And I'll get into Fargate a bit more detail. EKS plus Fargate integration is something that we are working on because that really needs to be done in an upstream compatible manner so that you can still continue to run your applications that are running on-prem and then bring them to AWS. And registry is, of course, a very critical part of where you push your application. And registry is something pretty much that you don't want to think about. I push my application, I want to download my application. If I'm doing 4,000 pulls for one particular image, in a second, it should support it. And that's the scale that Amazon ECR essentially operates at. So think of it from management, hosting, and image registry perspective. Those are the three ways by which we look at it. Now, let's talk a little bit about AWS Fargate, as I said. So AWS Fargate, as I said, what you do is you bring in a container, you write a task definition, which is Amazon ECS language. You need to create really a ECS cluster that is primarily for administrative perspective, but no nodes that needs to be added over there. You set up your thresholds. If you meet the thresholds, the number of replicas of the container automatically grow. Now, how does that work behind the scene? So let's talk about that a little bit. Essentially, what you say is, I want to run very much like Lambda in a sense. There are 40 different configurations that are available. So you can say, run this container with so much vCPU, so much memory. And that's all you say. And behind the scene, I'll talk about how that works. We allocate an EC2 instance and run that Fargate task for you. And you can see there are like 40 different combinations depending upon how much vCPU versus memory that you want. Okay? So how does that work behind the scene? Well, first of all, on the right side, what you see, there's a service account, which is the AWS service account. You never see that. But we have instances, a bunch of EC2 instances that are running in a warm pool. And we keep those instances ready for you. Now, you say, okay, I want to run, and you can see the blue, green, and the orange are from 3 different accounts. So now you tell us that, okay, run this Fargate task with so much vCPU and so much memory. We go behind the scene, we find out what is the closest matching EC2 instance. We bring that EC2 instance from the warm pool because it's already ready, primed for you to use. And then we run your Fargate task instance on that EC2 instance. If you say scale it, then we bring in more instances of that type, and then we run multiple. The key part here is to understand, because we are using EC2 as a virtualization boundary, so that's really one instance and one task is how we are running it. But from a user perspective, all you pay for is sort of the Fargate task. You don't see any of this happening behind the scene. You may realize that this is slightly inefficient for us because I may say quarter CPU and 2 gigabytes of memory, but there is really no EC2 instance that matches that type. So how do we make it more efficient? Within AWS, we're always looking at ways on how we can make our infrastructure more efficient so that we can do the saving and then pass on the cost to the customer. So let's take a look at that. So what we do is, with Firecracker, how does this game change? First of all, we don't need to have one Fargate task per one EC2 instance, okay? Because Fargate really allows you to say, tell me how much CPU, how much memory you want. I'm going to create a microVM for you. So you really take one task, you create a corresponding microVM for it, and you put the task into it. Then, because you don't need those warm EC2 instances, so all of that service account, that thing that we maintain on the back end for you, that is no longer needed here essentially, because the Firecracker microVM starts up rather rapidly, and as Meena talked about, 150 microVMs per second, depending upon the host that you're running, is totally possible that you can really create it on demand. And now what we do is we can take those big bare metal hosts and these microVMs, because it is using KVM as the underlying virtualization technology, that is sort of the security boundary as well. We can place all of these microVMs on a lot of bare metal hosts. And once you have placed them, very much like Lambda, we can actually do statistical multiplexing and place the workloads around so that not all CPU-intensive workloads are on one bare metal as opposed to all memory on one. We can do statistical multiplexing to say, okay, let's put the workloads together so that we're getting the maximum utilization of the bare metal resources that are being used behind the scene. Now, we have started deploying Fargate workloads. So if you're running in a particular region, depending upon where you are, you will be served by a Firecracker microVM in the backend. So because of the efficiency and the cost that we have seen internally in running our infrastructure, we did a cost reduction earlier this year, for Fargate. So if you're running a Fargate task, depending upon what CPU memory combination that you're running, we have been able to do 35% to 50% cumulative price reduction for you. No customers has ever complained that why did you put the price down? So we have done the price reduction over 70 plus times and passed it on to our customers as we have achieved those improvements within our infrastructure. And Firecracker is a way that enabled this. If you want to read about it, how we did this, here's a pointer to the blog, and the slides will definitely be made available. Meena also talked a little bit about Firecracker and Containerd. So let's talk about what that project is. Now, what we can do with Containerd. Containerd is a runtime which basically spins up your containers and is heavily being used in the Kubernetes land, essentially. So what we can do is we can use Containerd to manage your containers as Firecracker microVMs. So essentially, you have a Containerd process sitting up there on the top. Then you can tell Containerd that I need to run a container. Containerd will go run a Firecracker microVM for you, within which it's going to place your container, and then it's going to say, go run it. And I'll talk about the possible architecture that we are looking at it. The work is all done in open source manner, so you can definitely take a look at it. What it also enables is multi-tenant hosts. Because Firecracker gives you that security virtualization boundary, now Containerd can run containers from different customers on the same bare metal host. To maintain the upstream compatibility is fundamentally important that we use basically an OCI image format. So Docker is a popular OCI image format. And so essentially you can say, hey, this Firecracker Containerd integration is cool. I can bring in a Docker image. And now I can potentially run either a ECS task or a Kubernetes pod inside a Firecracker microVM. Because both of them, they end up using Docker image as the base. So our goal is to make it work basically both with Amazon ECS and EKS. So this work, as I said earlier, is being done in the open source. In the Firecracker repo, take a look at Firecracker Containerd GitHub organization in the Firecracker, in the repo actually, Firecracker Containerd repo, and that's where all the work is being done. We would love to see your thought process, how the design is evolving, what else would you like to see, what's working and not. So the goal over here is to define a future where we can have security and lightness all combined together. So you can get the security of virtualization and agility of containers combined together, being enabled by Firecracker essentially. So let's talk a little bit about the architecture here essentially. There are three main components. So there is a snapshotter, there is a runtime, and there is an agent here. So the snapshotter is basically linking Containerd to the Firecracker, which is you see right above on the top here, essentially. Now the Firecracker, the runtime is implemented as an out of process. Now if you look at this, on the right is where my microVM is. Both snapshotter and runtime are out of process essentially over there. And it basically communicates with a shim runtime using TTRPC protocol over there. It uses the VM disk image and the kernel image to spin up your microVM. So you say, that's how anyway Firecracker works. So you have to give it a kernel image and a disk image, and then it spins up your microVM over there. So once the disk image and the kernel image is used, your microVM is implemented or is started, then you have an internal Firecracker agent, which is basically listening for your Firecracker APIs that tell me what needs to be done. As we talked about, there is a bunch of REST APIs. Once the Firecracker VM is configured, then you can invoke those REST APIs, talking to the Firecracker agent to do the things that needs to be done in the microVM. So one of the fundamental things that we've been shying away, we don't want to call it as an Amazon Firecracker or an AWS Firecracker. We truly want to run this as an open source project. Sure, it was created as a need. It was created by Amazon and at AWS. But really what we are looking at it as a purely open source project. So we really want to hear from you. As a matter of fact, over 88 contributions from 32 open source contributors, which is about a quarter of the contributions are from external contributors. So Amazon is still one of the major contributors to it. I want to give a prop to actually Diana, who's sitting in the audience here. She's one of the Firecracker maintainers that have been working on the project from the very first day. We have any questions, please feel free to talk to her. She'll be excited to answer all of those for you. There are dozens of bug reports, feature requests, RFC feedback is truly and that's sort of where I play in because we have that customer empathy. I want to make sure this is truly run as an open source project. We do talks at different conferences, so we're doing more and more, not just doing the thing, but also talking about it so that we give an opportunity to talk to customers here. Another part that I am super interested about is Rust VMM. Now, if you think about, when we talk to our customers, they tell us Firecracker is cool, but here are like 5 different things I also want to add to Firecracker. And our tenets and the charter are very clearly defined on the project itself. So we want to make sure Firecracker stays true to its tenets and charter, but we don't want to deny those customers as well. So what we're doing is we are looking at the building blocks of Firecracker and moving them to this Rust VMM project. Firecracker is written in Rust. So what we have done is we're working with other industry players to create those VMM crates. So our long-term vision essentially is we want Firecracker to be a kind of microVM, which is built using those Rust VMM components or crates. So that now you have a need, you want to build a custom microVM or custom VMM, take a look at those crates, build your custom VMM, because that's where the work is happening. And that's essentially how we see Firecracker evolving in the future as well. So that's again a great place if you want to collaborate, if you are interested in Rust, talk to us, we would love to get you engaged over there. Talk about transparency. Literally, 3 days ago, I think? We have been working on this for a long time. So we did a RFC, like an issue, and we looked at customer feedback. What are the features that they want us to work upon? So there was a lot of discussions on the RFC, which was basically one issue. But about 3 days ago, we actually open sourced made completely public what our roadmap looks like. Now, you can see the categories over here are like researching, contributions welcome, upcoming. So at least you get a sense of what we are working on. And we would love to hear your feedback on this. What's working, what's not working, is it rightly categorized? So we want to be more transparent. And as we were discussing, the clarity is important so that you see clearly here what is coming out as part of this open source project. There's a lot of Firecracker integration that is happening with open source projects. Let me talk a little bit about that as well. Right after Firecracker was launched at reInvent, we had a very good meeting with Kata containers. And I'll talk about that a little bit more detail. But UniK is an open source project that basically takes your application sources and containers and create microVMs for that. So that's a cool project. There's a blog written on this on how you can use Unique to actually create a Firecracker-based microVM. So literally, you can take your application sources or containers and say, use the Unique and Firecracker integration to run a microVM for me. OSV is, again, a special operating system that is tasked to run a single application, very tuned for containers kind of an environment. Now, there is integration between OSV and Firecracker as well. OSV is different in the sense, if you look at a virtual machine, it's a very generic virtual machine that can run anything. OSV is tuned for containers in that sense. But again, with OSV, you can say use Firecracker as a mechanism to provision my microVM, and it'll do that. And vIgnite is a brand new project that was literally launched last week. So let me talk about that a little bit briefly about them. Now, Kata Containers is an open source project that is really targeting to build a lightweight VM for running containers. Okay, and it seamlessly plugs into containers. So customers have been using it. Now, Kata Containers has this concept of pluggable hypervisors. By default, it uses QEMU. Now, one of their biggest customer ask is QEMU is good, but it's very feature rich, very heavyweight. So they wanted a little bit more targeted, a lightweight hypervisor. And that's exactly where Firecracker kind of fits as part of their needs. So if you look at it, essentially you can use Kata containers to run in Kubernetes using lightweight microVMs. By default, when you say kubelet provision my pod, it uses CRI, uses a runtime class. Runtime class says, okay, by default, I'm going to use QEMU, go provision, run C, and provision my pod. But then what you can do is, you can say, use an annotation in your pod spec by which it'll say, oh, by the way, now I'm using Kata Firecracker integration. So in which case, it's going to go on the right side, where it uses a Kata runtime and uses a Firecracker VM, microVM, to provision your VM and then runs a pod inside that. So that's pretty cool integration. vIgnite. This is a project that I'm super excited about as well, because if you think about when we originally created Firecracker, our thought process was this would be primarily relevant for container orchestrator. vIgnite says that's not true, because that's where the innovation is happening. They say, Firecracker is a VMM. So we should be able to create a VM, and because you create quickly, we're going to leverage that capability. So it's an open source VMM with a container UX, essentially. So what you can do is, you can bring your Docker or OCI compatible images, and it'll create a Firecracker micro VM, and it'll run your OCI images in that micro VM, essentially. That really opens up a lot of possibilities. The primary possibility that that Weave is targeting right now, at least, is how you can enable a GitOps style, quick, where you do git push, you target to a Git repo, it builds your entire image, brings that Docker OCI image, runs it in the Firecracker micro VM. You can do quick testing, and that is possible because of the lightweight nature of Firecracker and how fast can it bootstrap. It's as simple as saying ignite GitOps repo. That's it. Just download the Ignite CLI, say GitOps repo, and you have to have the VM spec over there, and that's it. That's what enables GitOps for you. This is where you can find all the information about Ignite by itself. This morning, Radu actually gave a webinar with Weave Works on how Firecracker and Ignite looks at it. So if you're interested, I'll tweet the link again, and so take a look at that. So who should use Firecracker directly? Teams building compute services. If you are building container orchestrator, if you are developer and security engineers, that it matters to you, that you can use it. And again, we have seen more doors being opened because of vIgnite, that this is much more widely used. So getting started with Firecracker, you can use it either on bare metal. So I have done several demos around how you can fire it up on a AWS bare metal instance. It runs very well on nested wort as well. So Joe Beda did a TGI Kate series, and there he used GCP nested wort, and he showed how to run Firecracker over there. So whether it's bare metal, your laptop, wherever it is completely independent, is in no way restricted to a cloud. Very easy to get started with Firecracker. There is just like kube control, there is fire control. All you do is, I want to create a micro VM, you give it a kernel and a root driver, on a root drive. It basically takes that image, creates your entire micro VM with that layout and ready to roll. And you can, by the way, you can create your own kernel images and root systems as well. So feel free to use it. On the Firecracker repo, we have a link to a S3 bucket where we have a whole bunch of these root systems and kernels. So at least to get you started and play with them. Last but not the least, this is where you can find all the information about Firecracker. This is the Firecracker microVM GitHub repo, and that's where we want to collaborate and work with you. And as I said earlier, the internal and the external customers, we treat the same way, because even the internal engineering team is aligning with the external roadmap. So there is no such thing as internal Firecracker. This is what is one thing, everybody is conforming to that truth. Thank you very much. I would encourage you to rate the app, rate not the app, but the talk itself. Thank you so much.